Hi everyone. So in continuation from the first video, so this video is also going to be focusing on a few more examples of the second derivative test to classify functions as to classify critical points as maximum or minimum points. So I will share my screen. Okay. So in the previous video, we looked at quadratic functions or functions of parabolas, or parabolas. So here we are given a function y is equal to minus x cubed plus 3x, and this is a cubic function. So let's go ahead and find the critical points of this particular function. And for that, so let me actually just write this as f of x. Okay, so to find the critical points, we want f prime of x to be 0. And f prime of x is going to be minus 3x squared plus 3 is 0. So therefore we have 3x squared is equal to 3, x squared is 1, and therefore x is equal to plus or minus 1. And when x is 1, y is going to be what? Minus 1 plus 3, so you have 2. And when x is minus 1, we have y is minus of minus 1 minus 3. So we have 1 minus 3 equal to minus 2. So we have two critical points. When x is 1, y is 2. And when x is minus 1, y is minus 2. So far, so good. Fairly straightforward. We've just found out what the critical points are. Now let's use the second derivative test. Okay, so for the second derivative test, we need to first find out what f double prime x is. So let me just write that down. So if f of x is minus x cubed plus 3x, then f prime of x is minus 3x squared plus 3. And f double prime of x is minus 6x. Now, we need to find out the sign of f double prime of x, whether it's greater than 0 or less than 0, for the x values pertaining to each of our critical points. X is 1 and x is minus 1. Now let's go ahead and evaluate f double prime of x at each of these x values. So at this critical point of 1, 2, we have x is equal to 1. And at x is equal to 1, when you want to evaluate f double prime of x star, you want to do minus 6 into 1, and that is minus 6. And minus 6 is less than 0. And when your second derivative is actually less than 0, we are looking at a maximum. Therefore, the point 1, 2 is a maximum point. And we say it's maximum because we have the second derivative less than 0. At this particular point 1, 2, when the second derivative is less than 0, the function is concave, and therefore we have a maximum point. What happens at minus 1, 2? Sorry, minus 1, minus 2, right? That's our critical point here. So at minus 1, minus 2, my x value is minus 1. And if I want to evaluate my second derivative when x is equal to minus 1, I'm going to plug in x is equal to minus 1 into this particular expression. So that will be minus 6 times minus 1, and that is going to be plus 6, which is greater than 0. That is f double prime of x at the point minus 1, minus 2 is actually positive, which tells me that this particular point here is a minimum point. And that's because at that point, the function is convex, which is given by the second derivative being positive. And therefore, we have a minimum point here. Now, all of this is with calculus, but let's check if our answers are right by looking at the graph of the function. So So I will stop sharing this screen and we'll go back to the Desmos screen. Okay, so y is equal to minus x cubed plus 3x. This is the particular function that we are looking at. So let me choose this and let's see what the graph looks like. So this particular red line, actually red curve, plots the function y is equal to minus x cubed plus 3x. And it has a very interesting shape, right? It's not a straightforward U or an inverted U, but it's a very funny shape. Okay, funny is the wrong word, but it takes on an unusual shape. Now let's try and understand the behavior of the functions around the critical points that we saw. And remember, our critical points were at 1, 2 and minus 1, minus 2. Okay, so I've zoomed in on the function. And now you see how the function actually, so this is the point 1, 2. And you see the function has a maximum there. And this is a concave function. And you see how we have a maximum point there. It has an inverted U shape around this particular critical point. And similarly at minus 1, minus 2, it has a proper U shape here, and therefore this is a minimum point. So the graph actually confirms our calculus answers that we did indeed find the maximum and minimum points. So that was one example with a cubic function. Let's try another example. Am I sharing my screen? Yes, I am. Okay. So we're given another cubic function here. So let's go ahead and first find the critical points. So let me set y prime equal to 0. And my y prime is actually 3x square minus 18x plus 24 equals 0. So can I take out 3 here? So I have x square minus 6x plus 8, 0. So I think this is x square minus 4x minus 2x plus 8 is 0. So you end up getting, I think, this will be 3 into x minus 4 into x minus 2 will be the factors here. So therefore, we find x is equal to 4 or x is equal to 2. When x is equal to 4, my y actually just becomes 4 cubed minus 9 times 4 square plus 24 times 4 plus 10. So 4 cubed is what? 16 times 4 is 64. Minus 9 times 16 is, what is 9 times 16? 16 is 144. Plus you have a 96 plus 10. So this is minus 80 plus we have 106. So we get 26 here. Is that the right answer? Yes, it is. So 4, 26 is one critical point. Now when x is equal to 2, y is going to be 2 cubed minus 9 times 2 square plus 24 into 2 plus 10. So we have 8 minus 9 times 4 is 36 plus 24 times 2 is 48 plus 10. So we have a minus 28 plus 8, so we get 30. So 2, 30, yes, that's the next critical point. So we have two critical points, 4, 26 and 2, 30. Now let's go ahead and find the second derivative, and we'll try and understand the behavior of second derivative at each of these two critical points. Okay, so y prime is given by 3x square minus 18x plus 24. Note that you have, this is the actual expression for your y prime. Do not use just x minus 4 into x minus 2 because that is a simplified, that is when you factor it, and the 3 actually gets cancelled only when you equate this y prime to 0. But the original expression for y prime is, it does include the 3 here. So if you make a mistake there, your answers may end up going wrong. Okay, so this is y prime. Now y double prime is going to be what? 6x minus 18. Now let's evaluate this second derivative at each of the two critical points. Let's evaluate it at 4, 26. So which is, we plug in x is equal to 4 here. Now, if y double prime is given by 6x minus 18, and I plug in x is equal to 4, I have 6 into 4 minus 18. So this is 24 minus 18, 6. Therefore, at this particular point, 4, 26, my y double prime is greater than 0. That is, it is convex. Therefore, 4, 26 is a minimum. Let's look at the next point, 2, 30. Now here I will just plug in x is equal to 2. So y double prime is 6x minus 18. 6 into 2 minus 18. So 12 minus 18 is minus 6. And that is less than 0. So at 2, 30, we have our y double prime less than 0. That is, it is concave. Therefore, 2, 30 is a maximum point. Let's check if our intuition is right. Let's look at the graph. Back to, yes, this one's here. There it is. So the particular function we're interested in is right here. Okay, so let's zoom out and see how this function is looking. All right. Okay. So the curvature changes at these particular 2 points, and you see how this more or less looks very. I mean, this is another cubic function, and you see how this also has an interesting shape. And what are our 2 critical points? Our 2 critical points were 2, 30 and 4, 26. And you saw that 2, 30 is a maximum point, and the graph also confirms that. 4, 26 was a minimum point from our second derivative test, and the graph confirms that that is a minimum point. Now, so that brings to a close this example, and we now have visual confirmation that our answers are right. We've done the second derivative test, and calculus tells us that these answers are right. And if you actually check your notes, we used this particular function also in a first derivative test to try and understand how dy by dx will change its sign as it crosses each point, and all 3 methods have given us the same answer. So I will stop this particular video here and maybe do a couple more simple examples in a shorter video. And I hope these worked out examples are helping you understand how to put the second derivative test into practice. So I will see you in another video.